So for this problem, we have the same dimensions, but now we're ceramic. So if I'm a ceramic, I know my Young's modulus is around 300 gigapascals, not giga. My nu is equal to 0.2, so I could start to, I also have a negative thermal expansion coefficient of this. This is a typo here. It should be not room temperature, it should be 75 degrees C to 375 degrees C. So, and then the force applied is 30 kilonewtons. So, as we work through this problem, let's go ahead and let's write our values down. So y, actually, let's shrink it just a little bit. There we go. My y is equal to 300 times 10 to the 9. My nu is equal to 0.2. And finally, my alpha equals minus 37 times 10 to the minus 5. So I've got that thermal expansion coefficient. I've got there. I also have a force that's applied here in the 1, 1, and I'm constrained in the 2, 2. So let's start to look at the stresses. So my stress tensor, definitely got a stress in the 1, 1. My material is constrained in the 2, 2. It wants to ostensibly probably contract. So there will be a stress in the 2, 2. And in 3, 3, I'm free to expand. I'm going to ignore the edge effect. So I have no stress here. So my strain, however, let's see what's going to happen with the strain. I'm going to have a strain in the 1, 1. I don't have any strain in the 2, 2, but I do have a strain in 3, 3 because, again, the walls, I'm bound. Again, they're bound essentially to this problem. So I've got strain in the 3, 3. So let's go ahead and start to write out this problem. My del T is equal to 375 minus 75. And my ET is equal to alpha times del T. That's my thermal strain. And if I look at my thermal strain here, you'll see that it's quite significant. Usually you're looking at hundreds of microstrains, but this is quite a large strain value here. So let's go ahead and let's continue to work with this problem. So the force that's applied, so I need to write out, so I've got my stress tensor, so I also know that my sig 33 is equal to 0. Let's confirm that. Confirmed. I also know that my E22 is equal to 0, and there we go. So now I'm going to solve. I'm going to do my E11 set equal to 1 over y times my sig 11 minus nu times sig 22 plus sig 33. And then I'm going to go here, control here, here, and then E22, sig 22, sig 11, sig 3, E33, sig 33, sig 11. So when I look at this problem now, I have this, which I actually know. So let's actually plug in for sig 11. So my sig 11 is equal to, the force is 30 kilonewtons, so 30 times 10 to the 3. Make sure that's correct. Yes, that is correct. Divided by that cross-sectional area is 5 times 10 to the minus 3 times 500. So 5 times 500 times 500 times 3. There we go. So that is my sig 11. So again, 5 millimeters here, 500 millimeters here. Same dimensions as the last one. So that's my sig 11. So I know my sig 11. But I don't know what is my sig 22, what is my epsilon 11, and then what is my epsilon 33. 3 equations, 3 unknowns. So let's solve for those. So I'm going to solve for comma E11, E33, sig 22, and then let's do reals, even though we know we're going to get those values. And does this make sense? So I am, if I'm looking at my material, it is expanding in that 1, 1 direction, which is great. So there should be a strain that luckily I think is able to overcome that stress value there. Oh, we made a huge mistake. What do we forget? Which is I always unfortunately forget. I need my thermal strain. So be careful. So I need to add that thermal strain. And that makes more sense. Why? Look at how much this thermal strain wants to contract. So if I don't include that, again, our problem kind of looks similar to what we usually get. So I'm contracting the 1, 1 because that thermal strain overcomes that force. Same thing for the 3, 3. It wants to contract because there's there. And then there is a tension in the 2-2 makes sense because, again, the material wants to contract. This material wants to go this way. So the force to kind of maintain it at 0 is going to be the opposite direction. So it kind of makes sense. So my full stress and strain so my stress is equal to sig, what do I have here? I've got sig 11, what's my sig 22, which is this, and then I've got my sig 33, which is 0, for my strain, that's equal to this, no strain in the 2, but there is a strain in the 3, which is this. So I've got plane stress and plane strain, although in different planes. So what dominates behavior of the material? Basically my thermal strain. What is the shear modulus of this material? So my G is equal to my Y divided by 2 times 1 plus nu. That's my shear modulus, so if I ever needed some shear strains. Write out the principal stress and strain tensors. So I only have sig 11, sig 22, no sig 33. So if I want the principal, so I'm going to do basically solve for T dot, here's where I need to pull up my more transformations and more notebook. Can be very helpful. Linear algebra is awesome for sure, but I want to get to my T matrix. There we go. So let's pull this one in here, right above here, cosine sines. So I could do T dot stress, and I want basically, I want the third equation. I want to set it equal to 0, so I want my shear stresses to be 0, but you'll see I'm actually already at this principal stress state here. But that's how you would solve it for generally in terms of theta, so 90 again, 0, you're already there. So I'm in my principal stress state, so I'm already there. Same thing for my strain as well. You could actually look out those values, but I actually have to rewrite this notebook, so my actual strain will be this. If I'm writing the strain essentially in the notation of my strain is equal to epsilon 11, epsilon 33, and then epsilon 13, it would look like that. So principal stress and strain tensors, what's the maximum shear stress? So I can write that. So let's go ahead and let's put these guys right, this one right here, and then I'm gonna put this one here. So I am in my principal stress already, but if I want to go to my maximum shear stress, all I'm just going to do is rotate such that theta goes to 45. Again, I could solve that by looking at the derivative of this with respect to theta going to equal 0, and you could still solve 45. So that would be my maximum shear stress. Same thing for the strain, T dot strain slash dot theta goes to 45. And you see if I change 45 minus 45, it just changes that last value there. So got that. Write the full stress and strain tensors for 16 degrees clockwise rotation around the 3-axis. So again, I'm looking at 1, 2, 1, 2, and 3. So if I'm looking for rotation around the 3-axis, I am going to do basically 16 degrees clockwise. So for my stress, I'm in my plane stress state, so 16. So all I have to do for stress is T dot stress slash dot theta goes to minus 16 because clockwise is negative, and this would be my sig 11, my sig 22, and this would be my shear stress. So you see I have shear stress now, my sigma 1, 2. So those would be the 3 values that exist. Everything else is 0. So sig 11, sig 22, sig 12. Now, unfortunately for strain, we are not rotating around our plane. So I'm going to actually have to write out the full. So my full strain tensor, so full strain is equal to my strain in the 1, 1, which we definitely had. So my, going all the way back, my strain 1, 1 value. So there's the full strain. Strain 1, 1. There's no values over here. There's 0, 0, 0, and then finally there's 0, 0, and then this value over here, my strain of 3, 3. So this would be my rotation here. So that'd be my full strain. So in order to kind of write out that rotation, I'm going to have to look at, because we're doing a rotation around the 3-axis. So I need to look up, and actually I'll look up right now, basically rotation matrix around z-axis. So I can write, and this is actually a pretty useful tool. So I could look essentially right here. Here's my rotation matrix. Let's see if I got it. I'll just write it quickly so that we can work through our problems, which is right here. So I'm going to say my rotation RM3, actually RM3 equal to cosine theta degree, and then minus sine theta degree, and then 0, and then sine of theta degree, and then cosine of theta degree, 0, oops, 0, and then 0, 0, 1. So I need to find, unfortunately, so my 1 prime is going to be equal to basically my 1, 0, 0. I'm going to dot it with RM3 slash dot. Theta goes to minus 16 because that's our clockwise rotation. Look at that numerically. This, I could do 2 prime. I should do TP, but this is 1. This becomes 0. There's that. And if this is correct, if this rotation matrix worked, my 3 prime should be exactly the same. So let's see if that's true. It better be. Oops. And it is. So now I need to use my Q matrix. So let's go to Q. Let's see if we have that Q matrix. Here we go. So we have our Q right here. So I could go ahead and copy that in. So that's my Q. I need to clear what is C right now? I actually need to do CC. So I need to now find, unfortunately, so if we look back in our notes, we know that we essentially have that A, actually, let's go back to our notes here for a second. Let's check these out. Let's go ahead. And so I know A is going to be the angle between 1 and 1 prime. So I'm going to do solve for the angle between, I'm going to call this 1 equals 1, 0, 0. My 2 equals 0, 1, 0. And then my 3 is equal to 1, or actually 0, 0, 1. So those are my usual Cartesian coordinates. So I need to solve 1 dot 1 and 1 prime set equal to norm of 1 and norm of 1 prime, and I'm going to dot that with actually this norm times cosine theta degree, and solve. So my theta here is 16, so that A is equal to 16. You can write that down. 1 and B is going to be between 1 and 2 prime, so 2 prime, 2 prime. So B is equal to 106. You could probably do this in your head, but why risk it? 3 prime, it's not too bad. 3 prime, 90, so C is equal to 90. CC, be careful there. Again, 2 and 2 and 1 prime. 2 and 1 prime. Maybe C, D, 1, actually, it's 2 and 1 prime. So let's say that's 74. E, A, B, C, D. So 2 and 2 prime. 2 prime. 16. 2 and 2 prime. 2 and 3 prime. A, B, C, D, E, F, 90, and I think that 3 and 1 prime. Should be 3, 1 prime. These should all be 90. A, B, C, D, E, F, G, H equals 90. 2 prime. 2 prime. 90, and then 3. And this will be 1. 0. So A, B, C, D, E, F, G, H, I, and then J is equal to this. Make sure there's a J here. E, F, G, H, I was 0. There we go. So we've got those values. So now I could do my transformation, which is just going to be simply, so if I look at my strain, where's my full strain? Did I call that full strain? Full strain. So let's look at full strain. So full strain, matrix form. So that's my full strain tensor, so I'd need to do Q, or transpose actually, Q dot full strain dot Q. Let's look at this. Ooh, why is the G? A, B, C, D, E, F. Maybe there's a G equals 90. So let's just make sure. So G, I think I missed one here. C, E, F. G is the angle between 3 and 3 prime, or excuse me, 3 and 1 prime. 3 and 1 prime. So A, B, C, D. So F, so G is between 3 and 1 prime. F is between 2 and 3 prime. So let's do 2 and 3 prime. 1 prime. So this should be F. And F was 90, good. So I think we figured that out, but let's just double check with one more. So E should be between 2 and 2 prime. 16, okay, we got it. All right, so let's do that one more time. Let's look at this in matrix form. And we've got our big, beautiful, disgusting tensor. So these are basically 0, 0, 0, 0. So we have some other strains now. So aren't rotations wonderful? But now you know how to kind of work through those problems. Those rotation matrices are very helpful, actually. So now we're going to get into our last problem. So see you in the next video. Thanks. Bye.